Welcome to this short revision summary on gradually varied flow. We're going to look at three aspects. We're going to start off saying a little bit about profiles and profile sketching. We're then going to say a little bit about using a GVF table where we need to find the length of a profile. And then thirdly, we're going to look at those problems in which we are not given the flow rate and we must estimate it from the basic information given. First of all, what about flow profiles? Well, actually, technically there are 15 different profiles corresponding to horizontal, mild, critical, steep and adverse slopes. In practice, though, the only two that we really need to bother about are the mild slope profiles and the steep slope profiles. All the others are special cases of these two in general. So what about a mild slope? Well, it's defined as a slope for which the critical depth, the yellow line, is less than the normal depth, shown as the blue line. Conversely, a steep slope is one in which the critical depth, the yellow line, is above the normal depth, shown as the blue line. In normal circumstances, in a long channel of constant slope and roughness, the flow would be running at the normal depth, regardless of whether the channel is mild or steep. However, in gradually varied flow, the flow will be interrupted or prevented from running at its normal depth in general, except over certain parts of the channel. So, when the flow is pushed away from that, we end up with a gradually varied flow profile. Now, those profiles are identified by a letter, M for mild and S for steep, and a number, and that represents which zone of the flow the profile is forming in. So we will always have the channel bed. We'll have a line for the critical depth and a line for the normal depth. Obviously, in a steep slope, these two are swapped around. So we'll have the bed, one line, two lines, and then a region above the line. Regardless of what we're looking at, we identify those zones as 1, 2, 3 from the top down. So an M1 channel will be a mild slope channel in which the flow has been forced above the normal depth line here into zone 1, and we'll get a characteristic M1 profile. An M2 similarly is in zone 2, an M3 in zone 3, and the same thing for S1, S2 and S3. Those 6 profiles we need to be familiar with. We need to be able to sketch them out as shown here and identify them. So let's look at a typical example in which we're asked to try and sketch and name the surface profiles which occur along this channel. Typically we'll have two different slopes. Here it's going from steeper to flatter. It could be going from flatter to steeper. And we often have a termination point for the channel shown here. So the channel ends here, the flow just passes over the end. And we usually have a structure of some kind. Here it's a gate, and we're given the gate opening above the channel bed. Sometimes it's a weir, and in that case we will be given the height of the weir above the channel bed. So some kind of structure that's going to interrupt the flow. The first thing we can work out is the critical depth. That's given by the cube root of q squared over g, where q, little q, is the total flow over the width of the channel. So this little q applies as whether we have a wide channel, as we have here, or even in a non-wide channel, little q would be the total flow over b. Just as a reminder, if you look at the formula sheet at the back of your exam papers, you'll see that this is a formula you would be expected to remember because it's not given there. So be careful about that. Now, yc, as you can see, is a function just of the flow rate. So its value, which we got here, 1.366, is going to be fixed all the way along the channel. The normal depth, however, will vary. It's a function of the slope as well as the roughness. So we'll get a different normal depth along here as compared to here. Now we also need to remember that for a wide channel, which is what we're given here, we can write Manning's equation in terms of the flow per metre width as 1 upon n y to the 5/3 s to the half. In other words, we're making an assumption that the hydraulic radius is equal to y, and of course the area of the channel is y times 1. So we have 1 upon n y to the 5/3 s to the half. It's very useful to have a wide channel because it means we can calculate the normal depth y directly. So if we separate out y, you can see y is qn over s to the half all to the 3/5. And we then find then that y naught AB is 1 metres, and along BD it works out at 1.62. So if we compare AB, we can see the critical depth is 1.37, the normal is 1, so the normal is below the critical. According to our classification, that would be a steep slope, and then BD, it's the other way around, the critical 1.37, the normal 1.62, it's above the critical, so that's a mild slope. We could go now and illustrate that diagrammatically on our sketch. Here's the critical depth, constant all the way down, and it's above the bottom of the gate here, as you can see, and then the normal depth below YC on AB and above YC on BD. So this is steep and this is mild. So even at this stage now, we could sketch in some of the profiles we know that are going to happen. The flow entering the channel will have to pass through the critical depth at the entrance. So in attempting to get to the normal depth, it will find itself in zone 2 of a steep slope, so we'll have an S2 down here. Go down to the bottom end, work back up from the overflow point. Back upstream, the flow would be, it'll pass through the critical depth again, somewhere around the exit, so it will be in zone 2 of a mild slope, so we'll have an M2 here. When it comes out from under the gate, it's on a mild slope, but it comes up at a depth lower than the critical depth, because the gate's 0.9 and the critical depth is greater than that. So we'll have a length of M3, and then behind the gate, the flow will be lifted up above the normal depth, so we'll have an M1 going back here. So already we can sketch in 4 different profiles. Now there is often a helpful phrase in questions. It says, assume the sections are sufficiently long for uniform flow to be established. So we don't have any information about the lengths of these, but we're just saying that yes, if there is a normal depth line, then the flow will get to it and it will carry on at that normal depth for some distance, maybe a very short distance, maybe a longer distance, we don't know, but we do know that it will get to it. In general, sometimes profiles, only a small part of them form before they're then interrupted and begin to become some other profile. But here we can assume that we'll get to the normal depth here, we'll get to the normal depth here, we'll get to the normal depth here. And that's very common in these kinds of problems because it saves us having to speculate whether or not the profile will reach the normal depth. Of course, when a profile has to cross the critical depth line, as it does here, it has to do so by means of a jump. So we have a jump here, and we've also going to have a jump somewhere here because the profile is at the normal depth here and it's at the normal depth here, but this normal depth is below critical, this is above critical, so it will have to form a jump. Now it's very common to put in this element into a question because actually there are 2 possible routes for going from this normal depth to this one. In fact, we could get from here up to here by having a jump on the steep slope, and then as soon as we cross the critical line, the flow would have to join up here by means of an S1 because it would find itself in zone 1 of a steep slope. Alternatively, the flow might carry on here onto BD, and then it would find itself in zone 3 of a mild slope, so we'd have a bit of an M3, and then at some point we'd jump across up to this normal depth here. How do we decide which of these 2 is going to happen? and that's what this part of the question is, indicating the location of any jump. So if it says indicate a location, it just means we have to say where it's going to happen. If it said calculate the distance of any jump from B, for example, or C, then we would have to not only identify where the jump was occurring, but also do a gradually varied flow length calculation, which we will talk about later. So how do we make the decision as to where the jump's going to happen? Well, basically all we have to do is to choose one of these two possibilities and do a little bit of a calculation. If we have a hydraulic jump and we know the depth on one side of the jump, we can use the hydraulic jump equation to find the depth on the other. So, for example, if we assume the jump was here, we know this depth is the normal depth on AB, we can use the jump equation to find the depth just on the other side of the red line. Now, we know that we would have to have an S1 forming here, so increasing in depth and joining this normal depth here. So this depth just on the other side of the red line would have to be less than this depth here. Okay, and remember we've got very exaggerated bed slopes here, so we shouldn't be sort of put off by that. In practice these are relatively flat, and over a short distance they don't have too much influence on the problem. Alternatively, if we chose this as our test, we thought the jump might occur here, then this would be the known depth after the jump. We'd use the jump equation to find the depth before the jump. And because we know that if this was to happen, we'd have to have an M3 in which the flow would be increasing from its depth here. So when we used the jump equation and found the depth here, it would have to be bigger than the depth here. So either way, we've got a test, and all we have to do is choose one of these options, do the test. If the test works, then that's what's going to occur. We don't have to check the other one. If the test doesn't work, then it means that we've chosen the wrong option and it must be the alternative. So here we're going to make the assumption that the jump occurs on BD on the downstream section. We know what the depth after the jump is. It's the normal depth on BD. So we're going to use the jump equation to find the depth on the upstream side of the jump, i.e. just when the jump is about to occur. That is, we're assuming this one, so we know the depth here, it's the normal depth here. We're going to use the jump equation to find this depth, and obviously we need it to be bigger than the depth here. If it's bigger, it means this will work, and this is what we're going to get, and the other one wouldn't work. We don't have to go and check it. Now the jump equation, which in fact is given in our exam formula sheet, can be swapped around so that the depth we want could be the depth before, in which case everything on the right hand side has the subscript 2 conditions on the downstream side, or if it was y2 we wanted to find, we'd put y2 here and then everything here would be y1. Well, in this case, as we said, it's y1 we want to find. y2 is the normal depth on BD, so we know what that is. We need to calculate the Froude number of the flow downstream, and then we can find out what y1 is. Now the velocity on the downstream side is q over y. Q is 5 cubic meters per second per meter width. Y on the downstream side of the jump on BD is the normal depth that we've worked out here, 1.621. So the velocity is 3.085. The Froude number is the velocity over root gy. Okay, so this is the velocity over root g times y again, which is the normal depth on BD. So we've got the Froude number, we put it in the jump equation, and the depth we get is 1.139. So 1.139, this is the depth we've calculated from the jump equation. If we go and look at the normal depth on AB that we worked out, it is 1. So that works because we're going from 1 to a depth greater than 1, 1.139. Not a lot, but that's sufficient. We have a little bit of an M3 here and a jump up to the normal depth here. If I'd worked this out and it was, let's say, 0.85 or 0.9, that would tell me that it was impossible to have this particular scenario, so this is the one that would actually occur. So finally, looking over the page, here's the diagram of the whole story. We know what it is already, of course. The profiles to be sketched are an S2 down here, a little bit of an M3 here, jump across here, an M1 behind the gate, and then coming out from underneath the gate, an M3, jump across here, and a bit of an M2, and back over the free overfall through the critical depth here. And that's it. So the principles that we've outlined again here are going to be the same in any curve sketching problem. And the only thing that we may have to do, which we haven't covered here, is to actually calculate a specific distance or length of a profile. To do that, we'd have to use a gradually varied flow table, and that's what we're going to look at in the next section. So if we do have to try and calculate the length of a profile, we use this expression here, delta x equals delta E over S naught minus S. It's an expression which is included in the standard formula sheet, by the way. Now, what do these terms mean? Well, take a profile here, for example. This could be an M1. What we do is divide it into sections. How many sections? Well, we need to know a starting depth and a finishing depth or section. And then in between, we should aim to go for 3. So that would give us 5 sections, 4 increments. But if we're pushed for time, we could go for a start, a finish, and 2 internal sections. That would give us 4 increments, but 5 is the best compromise to aim for. Now, in our table, as we'll see in a minute, what we would do, draw up a table. We have the starting and the finishing depths. We have our intermediate steps, which we choose, and we calculate for each of these sections the specific energy, E, y plus v squared over 2g. And we also calculate the slope of the total energy line at each section from Manning's equation, that's SF. And the bed slope is S0, so that's the slope of the bed here. What is SF? Well, if we look at the water surface and we can draw a line that's v squared over 2g above it everywhere, that's known as the total energy line. In a profile such as this, which is increasing in depth as we go along, that means the velocity will be decreasing. The velocity is q over y. So as y increases, v decreases. So that line will be getting closer to the profile. If this was a profile that was decreasing in depth, of course the opposite would be true. But that doesn't matter really as far as working out the length is concerned. If we were to try and estimate the slope, or more specifically the slope of the tangent to this total energy line at a given section, that would be SF. So we will get a series of SFs at each section. They'll all be slightly different. And the SF bar is the average of these two adjacent sections. So it's the average slope of the total energy line between a given pair of sections. Okay, well, how do we set this up in a table? Well, here's a typical table with some columns here. So we have to enter our starting depth, our finishing depth, and our 2 or 3 intermediate sections, 3 preferably. We need to calculate the velocity. If we're talking about a wide channel, the velocity would be the flow per meter width over y. The specific energy will be y plus v squared over 2g. Delta E will be E on E1 minus E2, so there's no value in the first line, but in the second and subsequent lines it would be the E here minus the E here. Sometimes that's positive, sometimes it's negative. It depends on whether the profile is increasing or decreasing, whether E is increasing or decreasing along the profile. It doesn't really matter if they're all negative. What we shouldn't get is a switch from negative to positive or the other way around. That means we've made a mistake somewhere. And then SF would be calculated from Manning's equation. So if it's a wide channel, Manning's equation expressed as the flow per meter width for a wide channel is little q equals 1 upon n, y to the 5/3, making that substitution for are y to the 5/3 s to the half. So therefore s would be q squared n squared over y to the 10/3. And we're using it here to calculate the slope of the total energy line, so we put a little f there. So that's where that comes from. SF average, as we've said, nothing in the first line, but second and subsequent lines will be the average of these two there. And then delta x, the distance between any pair of sections, delta E over S0 minus SF bar. If we did happen to have a non-wide channel, so that was a channel with a defined width, and we weren't able to assume that it was wide, then it would be exactly the same table. The velocity would then be q over by, b being the width of the channel. And here, SF, we would be using the non-wide version of Manning's, so q is 1 upon n, a to the 5/3 over p to the 2/3, s to the half, so the bed slope would be q squared n squared times p to the 4/3 over a to the 10/3. So a little bit messier to work out, but otherwise exactly the same process. Only other thing to mention about doing these tables is that there is a little rule as to the order in which you put the start and the finish sections. Basically, if you've got a subcritical profile, so that would be an M1, an M2 or an S1, then we work from the downstream end of the profile back upstream, regardless of whether that means that y is increasing or decreasing. Obviously in an M1 we have a bigger number here, and in an S1 we have a bigger number here, and we end up with a smaller number here. In an M2 we would have a smaller number here, and we'd end up with a bigger number here. So subcritical profiles, M1, M2, S1, should go from the downstream end in an upstream direction. If we had a supercritical profile, you can check back on your diagrams of profiles to confirm it, that would be an S2 or an M3 or an S3, then we would be starting at the upper end of the profile and putting our sections in a downstream direction. The only purpose of doing that is to minimize errors. So if you get it wrong, it may not have much effect on the answer, or in other situations it might have. Okay, well, the final part of this summary is looking at those problems in which we have to estimate the flow rate. So no flow rate given in the question. All we will have are basic details about the channel, about its slope, roughness and section, and also some information about the head at the entrance to the channel. That would be the lake or reservoir that's feeding the channel. If we assume the velocity in the lake or reservoir is very small, then E is equal to just the physical head above the invert to the channel here. And if we make an assumption that the losses as the flow enters the channel are very small, and we go a short distance downstream, and we ignore the slope of the channel, which we've obviously drawn in a rather exaggerated manner here, then E downstream a short distance is effectively the same as E here. So we can look at this section here and form some conclusions about what happened. Okay, so if we think back to what we mentioned briefly in the second year, if we have a channel which at a given section has a fixed value of E, so we're thinking about a point just inside the entrance, and we were to plot how the flow rate varied against a range of possible depths, then we get a curve like this. And we find that there's a maximum to this curve, Qmax, and that corresponds to the critical depth of flow. So in a sense, this is a range of possibilities of flows that we might get at that point just downstream of the entrance of the channel. But of course, once we're in the channel, Manning's equation should also generally be applicable, assuming we haven't got into non-uniform flow very quickly. So Manning's equation can also be plotted as a shallow curve of Q versus Y, and we'll see that it will intersect this curve at possibly a point here. On the other hand, when we plot Manning's equation, the curve might come way over here. So what does that mean? Well, if the intersection is somewhere between this point and the maximum, then the actual flow we get would be given by this intersection point here. If Manning's equation does not intersect between here and here, but intersects between here, or conceivably doesn't intersect at all, then the flow we get is not this one here, it's the maximum, because it is a fact that the maximum possible flow you can get out for a given E is this point here. Once you've reached that, you can't sort of go back down this line here. So this part of this curve is not really physically available to us. So how do we go about determining the actual flow? Well, the first thing we do is we assume that the slope is steep. That means that the flow we get would be the maximum, because if the slope is steep, the flow will have gone through the critical depth somewhere near the entrance. So yc is the cube root of q squared over g, so we could find q if we knew yc, and of course yc is 2/3 of E. So if E is the head available in the reservoir or lake, yc would be 2/3 of that, so we can calculate q. That would be q max. So that would be the... Now, to see whether that is the flow or whether it is something less than that, we do a little test. We take Manning's equation, we put y equal to yc in it, and if our plot of Manning's equation were over here, we would intersect with a test value which was less than q max. Alternatively, if Manning's equation when plotted was actually over here, we would get a value of flow q test which was greater than q max. So by putting y equals to yc in Manning as a test, we'll get a test value which is either less or greater than q max. If it's greater than q max, it means we do have a steep slope and the actual flow is q max. If it's less than q max, it means we have a mild slope and the actual flow will be this point here, and we will have to find it. How would we find it? Well, Manning's equation is V equals 1 upon n r to the 2/3 s to the half, and this equation here is E equals y plus v squared over 2g. So if we substitute for v from Manning's equation in there, we'll be able to solve for the depth and the flow at this point here. Just to see how this works out, let's take this problem here which has got an E of 3 meters at the entrance to the channel, and let's just see how we would estimate the actual flow. We're given the slope and we're given Manning's n. In this example, actually, we have a non-wide channel, so very slightly more involved than if we had a wide channel. But the first thing we do is calculate yc. It's going to be 2/3 of E, so E was 3, so that's just 2. And then we know that yc is the cube root of little q squared over g, and if it's not a wide channel, then little q, we write it out as q squared over b squared g, and yc will, that will allow us to calculate q, because we know yc is 2, and q comes out to be 44.3. So that is the maximum possible q we could have for that given E. So let's just see if the flow is actually the maximum possible, or is it something less than that. We'll put y equals to yc in Manning's equation to get a test flow. Now Manning's equation for a non-wide channel is big Q equals 1 upon n a to the 5/3 over p to the 2/3 s to the half. A is b times y, p is b plus 2y, and the test y we're going to use is yc, which is 2. And if we put these values in there, we get that q is 32 cubic meters a second, less than the 44.3 maximum, so therefore this is a mild slope, and we will have to find the actual Q by taking the energy equation, E equals y plus v squared over 2g, and substituting for v from Manning's equation. In this kind of problem at this stage, it's actually better to just leave the velocity v term in the expression for E, and also express Manning's equation in its basic form as in terms of v. So we don't need to write y plus q squared over 2g y squared or whatever, and neither should we express Manning in terms of the flow rate, not for this particular substitution. So we're not going to use this version, we're just going to use this version of Manning's equation. So v is 1 upon n r to the 2/3 s to the half in its basic form, Manning's equation. So that's the bit we're going to substitute in for v squared. So that would be y plus, we square all this up, r to the 4/3 s over n squared, and then we've got a 2g on the bottom line as well. R, of course, is a over p, which for this rectangular channel is by over b plus 2y. So we can only solve this by trial. We want to get E equals 3, so we're going to have to choose or try and find a value of y that will give the right hand side here equal to 3. Usually it's easier to have a column for a column for p, and then r is a over p, and then take that r and put it in here, okay, in this expression here, where we've substituted Manning's equation into the v squared over 2g term. Go for 2.5, and it's a little bit bigger than 3. The answer after a few trials, 2.406. So we find the actual y, and then we can go back to Manning's equation and find the actual q. So finding the discharge is a standard procedure, and we've just outlined how it is done, and the illustration and the numbers we're using were part of this question, and we may as well just look at the rest of this particular question just to illustrate a further thing that we are often asked in such questions, and that is, what if we have a downstream structure? Will the flow that we've just worked out be affected by the presence of this downstream structure? In this case it happens to be a weir, and we were told what the depth was immediately behind the weir. So we've decided it's a mild slope, we've calculated the normal depth, 2.406. We see that the depth we're told we get behind the weir is bigger than that. That means the flow has been pushed up into zone 1 of a mild slope, so we get an M1 profile back upstream. So what we have to do then is plot that profile between the depth we're given, 3.1, and the normal depth y0, and if it gets to the normal depth over a distance that's less than the distance we're given from the structure to the channel entrance, then of course the flow from the lake into the channel would be unaffected. But if we find that over this distance we still haven't got back to the normal depth, what that means is that we cannot sustain the flow we've calculated with this head, so the flow will actually be less. So we'd have to go back and try all over again. You won't be asked to do that in an exam question. The most you'd be asked to do is to check whether the flow that we worked out in the first part is or is not going to be affected by the introduction of a particular structure downstream. In this particular example, we set up the gradually varied flow table. It's an M1, so we start at the bottom end, it's a subcritical profile, so we have 3.1 here, and then we put the normal depth in here, and we work out the distance from this depth to the normal depth, and it's 1100 meters. That's a long way beyond the 400 meters we've got here. So the flow that we worked out, 41 9.1 is not going to be sustainable. We'll have to drop down some way below that. So we'd have to retry again with a lower flow. So we're not really going to look any further at that. As I said, we don't need to do that, we won't be asked to do that, but we should be able to suggest how it could be done if necessary. Well, that concludes this brief revision summary of gradually varied flow.